Today I have Joe Lewis with me. Joe's with Baker Hughes Masoneilan, and Joe is the Global Product Manager for Engineered Products. You guys all have these long titles, man. I always got to do my cheat sheet on my whiteboard here. So, Joe, welcome to my podcast.
Hey, glad to be here. How's it going, Bill?
Doing well, man. Doing well. Joe and I were talking, and a lot of times when guests come on, I have a frame meeting. And Joe's been with Masoneilan for almost 20 years, and he's been in business for over 20. He's a manufacturing engineer out of BYU. And we were framing on, hey, what do we want to talk about? And Joe suggested, hey, Bill, let's talk about erosive valve service. So we're going to talk about erosive valve service. We're going to talk about the causes, and we're going to give you some solutions on how to handle erosive valve services. And Joe, why don't you take it away a bit, and I'm going to interject as we go along, and we're going to have a little bit of a dialogue. But let's talk about erosive service.
Sure, it's really kind of a cool application because normally you don't see a lot of it.
Okay.
Out in the field, but you know what? Over the past 5 or 6 years, I've been seeing a lot more applications out there where a different type of valving is required, or at least you can't just run your sizing program and say this is the valve that's going to work, because of the fact that there's erosive things going on with the valve. And the thing that we needed to do was really understand what are the mechanisms that is driving the erosion. And knowing those mechanisms, you can actually come up with the right technology to apply to handle those issues. And so we were taking some time as a company to delve into the applications that we see out there, what we see in the future, because I know you probably have seen as well, applications are changing out in the field, higher pressures, higher temperatures, different feedstocks are being used. There's a lot of things that are going into what you would not normally see, say 10 years ago in the business.
That's true. I mean, like I have a major refinery in my territory, and a lot of times their application data has changed a lot since when the valve just went in 10 or 20 years ago. Exactly.
It's a combination of feedstocks. We have, in North America, you have feedstock coming from Canada, which is completely different than what the States are used to. You have a lot of stuff that's coming from China that they're using different feedstocks. They're using IGCC, coal gasification to do oil, and, to do their business. So there's a lot of things that are coming out in terms of having to adjust the way we look at applications and make sure that we are choosing the right technology to handle those issues. So I kind of want to go through this. I'm actually, believe it or not, I'm in the middle of writing a white paper about this, and I will pull up a couple slides that kind of go into our the actual applications here. So,
hey, just a side note.
Yes.
How long does it take you to write a white paper, man?
You know what?
Is it like 6 months, or it's a pretty long process, isn't it? It is. A sidebar real quick, but then we'll go. So got it.
Yeah, it has taken me a lot longer than it should have, believe it or not. I've gotten the hard parts done, the hard parts, which is looking at the actual mechanisms of erosive service, and I'm right now I'm in the middle of writing the easy parts, which is, hey, this is the technology you should use for this type of application. Here's what you should use here. And so
I always liken it to somebody writing like their doctorate thesis or doctorate or something, and there's a lot of details in those things. So
you know what? I have a lot of great resources within the company to pull. We have a lot of great principal engineers that are extremely experienced in this, that can give me the nitty gritty details that need to go into white paper. So, so when we talk about severe erosive service applications, we really have three main erosion types that we're looking at. And first off, we look at flashing, because flashing is really is one of those ones where there's not much you can do within the valve to get rid of the flashing. The flashing is there. It's not like cavitation where you can design a trim to eliminate the cavitation, which we do on a regular basis. Flashing is always going to be there. The fluid is below the vapor pressure. You have flashing. Peace. At that point, you need to say, what is the criteria of flashing and what makes it, moderate to severe? What are the criteria that you should look at and make decisions over? And so we really look at percent flashing that's occurring within the application. And typically, flashing percent, say 5% or less, is we really call that a, minor flashing. There's not enough energy or not enough energy that's being dissipated in that to really affect the trim or the interior of the valve in much of a way that you would need to do much in terms of technology selection.
Okay.
So that, and it's very easy to come up with percent flashing. As long as you know the fluid properties and you can size the valve, it'll give you percent flashing. We do that regularly.
Okay.
If you have flashing between 5 and 10%, we call that moderate flashing. And at that point, you need to take some pretty basic considerations when you start talking about valve technology. Whether you put in, and there are things like, changing it from a globe style to an angle style. When you have that ability to do that, okay, you're actually directing the flashing away from the control valve into the downstream. You have a lot of ways that you can direct that in a much better way, or you can just do something as simple as putting hard material inside the valve to dissipate that energy. Very, very simple, simple things that we can do. When you start talking about 10 to 25% flashing, which gets to the point of being violent flashing, that's when you start to take into account real technology changes. Going in, a must would be going to an angle style design. At that point, you'd start talking about Venturi outlets. You'd start talking about different types of materials that you're going to use for your control valve. You're going to start looking at all those things that will take that violent flashing and either direct it into an area where it's going to be benign, or you're going to direct it into an area that can handle the violent nature of that flashing with minimal damage. So those are the types of things you start to look at. So, you can easily calculate percent flashing. Once you do that, you can start tailoring your technology to a technology that really is going to work.
Okay. When you talk about violent flashing, is there an application that jumps out to you that like happens to like in that
Sure.
violent flashing?
A lot of them are like a tank drain. A lot of times you have, it could be, a fairly, high pressure tank, or even a low pressure tank for that matter. That's got some heat to it. That's not, at room temperature. It could be a couple hundred degrees. That's going straight to atmospheric condition. Okay. When you have that type of application, you're basically saying, I'm going to flash whatever this fluid is across the control valve. It's going to happen. And that's when you start to take a look at, okay, what do I need? And, you may have 2 to 3 different technologies that you can use, but then you start to look at the application. Tank drain, it needs to be a tight shut-off valve. So you shouldn't be using a valve that is okay if it leaks, just as long as it's mitigating the damage. Mm-hmm. You want to start looking at something that is very good at tight shut-off, and as well can continue to mitigate the damage so that you get long life with that shutoff. So there's compromises here. You could choose a technology that's fairly low cost, and that would be great for one application but horrible for another. You may have to spend money for a higher end technology in order to meet the application that you're looking for, whether it's tight shut off, or whether it's just longevity. You've got some issues to understand with the specific application, not just the physics of the application.
Okay.
Second one is abrasive particles,
Mm-hmm.
and this is what I would say is the most common when everyone talks about erosive service. They think, oh, there's particles in the line, there's trash in the line, it's eating up my valve. Mm-hmm. And that's in most cases that is true. But there again is where we start to take a look at what does it mean abrasive particles, and what does it mean for the application. You've got a lot of choices when it comes to abrasive particles. It could be high percentage of abrasive particles in a slow moving slurry application, or you could have a very small amount of abrasive particles in a extremely high velocity application. You've got that breadth of what is it, what is the application, what are the physics of the application, and again, what do you take a look at what you as opposed for technology really is to say, hey, I can put in a valve here that I would work great for a slow moving slurry application, but would last probably 30 minutes in another application. And you could have another valve that would cost $100,000 and be put in a $5,000 application that would work just fine if you put in a lower technology valve. So you really got to understand again what the application is looking for. In a typical abrasive particle application, we really talk about it becoming an abrasive application when there's 0.1% by weight of abrasive particles in the fluid stream, and that doesn't seem like a lot. But when you start talking about sand particles or catalyst fines or anything like that, depending on the application, that could still be quite a bit if it's flowing at high rates of velocity. So what we really look at in these cases is we look at a combination of the abrasive particles as well as what type of particle it is, and then what type of material we start talking about using in whatever our technology is. You could use a technology that has a very smooth flow through design because you don't need to handle a pressure drop, say. And if you use the big flow through design, you could use a very brittle material like ceramics or something like that. But let's say you had to do a fairly significant pressure drop, and you had to take pressure stages, a number of pressure stages in the valve to handle the staging or to handle the pressure drop. At that point, you start seeing, hey, I don't want to use a brittle material because what we call the angle of impingement, the angle that particle is going to impinge on the actual hard surface, as that angle gets closer to 90 degrees, you get more wear. And so we found that this chart here shows that depending on the technology of the valve or the actual geometry of the interior of the valve design, as well as the trim, ductile iron could be better than the case of, say, a ceramic material, like a brittle material. And so you have to really take into account what the materials are as well as the valve design when you start talking about abrasive particles, because you could have one that works great in one application and you put it in another and it wears out 10 times as fast as you would think. It's just because it was misapplied. And again, that's what we're coming in is looking at the physics behind it, and then looking at what type of product design you need to actually put forth, the technology.
Yeah, and I think if I'm an engineer, right, and I'm the customer, and I go out to 3 manufacturers and I say, here's an application, I could get 3 very different solutions to this based on that manufacturer and the way they approach these solutions, correct?
That's absolutely correct. And along the same lines, you could have 3 completely different applications and get the same valve applied to each one of them. So
Okay.
it kind of goes both ways. It's saying, hey, you know, I've got 3 different applications, and you cannot apply the same valve to all 3,
Right.
as well as going back and saying, hey, I've got this application. I've got to understand what the valve technology needed to handle the application is, and whatever I'm getting back from my vendors should apply to that, as opposed to just being what they have on the shelf for one specific application.
Right. Okay. Go ahead.
Let's see. The next one is velocities.
Velocity. Yep. This is one I run into quite a bit. So go ahead. Go ahead.
Yeah, absolutely. Because I mean, this is typically what you see out in the field is on the extreme ends of any type of erosive services. You'll see typically it's a combination of velocities and particles. But when we start to talk about fluid velocities in a control valve, we really need to understand that normal rules don't apply.
Mm-hmm.
So normal rules are for normal applications, at least from our standpoint. We kind of follow we follow IEC. Our sizing program delves into it as well. Is we pretty much limit our fluid velocities within a control valve to 30 feet per second for liquid applications.
Yeah.
For the most part. And so that's great. That's great for normal applications. That's great for your feed water research, your level control valves, your feed valves. All that's great. But when we start to talk about erosive services, we have found that 30 feet per second is in terms of erosive service is extremely high velocities. It may be great when it's a clean surface, but when there's particles, you really need to back off the maximum velocities that you normally put into a valve. And what we're talking about is we're talking that we back off to between 5 and 10 feet per second when we start talking about fluid velocities in an erosive service. It just pulls back so much of that energy. And typically what you're going to see happen in some of the technologies is your valves can get bigger. Quite honestly, your valves can get bigger because you're trying to limit the velocities. You could use multi-stage trim to back off the velocities as well. So there's a lot of those things that you really need to do. If you can't reduce the velocities, then you need to use a technology that directs those velocities in a way that you say even a sacrificial material, sacrificial say Venturi or something to those points where you say, you know, I can't take the velocity down to the needed levels. So in this case, I'm going to build my technology around this fact and build a technology that's going to come in and handle that velocity in a way that's acceptable to the customer. And it's acceptable to say, hey, you know what? I know that I'm going to have to go into this valve, say, every 18 months, but guess what? I know what part's going to be needed to be replaced. I can have one on the shelf. I can just go in, replace the part, and go. And it's something that can protect both your upstream and your downstream. You can protect the valve as a whole, and it can protect your downstream system as a whole. So there's technologies here that we really try and put into place to handle these 3 types of erosive services.
Okay. And Joe, a quick note on the velocity. I know that's a pretty critical measurement when you're sizing a control valve. And just a point here, but I know either one or some of our major competitors don't put velocity in their sizing program where we do. And I know when we're sizing a valve, we emphasize that with customers. Hey, check your velocity.
Yeah.
So, I mean, that's a pretty important figure to have in your sizing program, I would think.
Yeah, velocity is always one of our main results that we publish in our sizing. Between velocity, CV, noise calculations. I mean, there's half a dozen basic calculations that need to be done in order to properly size a control valve.
Yep.
And if you take into account four out of the 6, great. But guess what? You can get burned on the other 2. And we just know that it's for us. We have to take into all of those into account when we're looking at a proper selection.
Okay. All right. So you've got some solutions to these problems, right? On your next slide.
Sure. So just to look at some of the solutions, and what I kind of want to kind of impart here is not everything here has to be the most expensive, highest technology product, in the portfolio to meet those applications. This one right here is our CamFlex. I mean, almost everybody in the industry knows the CamFlex. It's a great valve. It's extremely versatile.
I love the CamFlex. I just want to say it. There you go.
But in these cases, it doesn't get a lot of love because this is a inexpensive valve. It's great for low pressure water. Great. No, that's not it. This valve is very versatile. And it's designed that you can put a bunch of different trims in it. We can put stellites in it. We can put ceramics in it. It's a flow-through design, so there's very little impingement for any of the fluid or any particles that would be going through it in this valve. I have one of the great applications I put this in was I had a customer up in Central California he said, I mine dirt. So I'm going to take the dirt, I'm going to liquefy it, I'm going to pull some minerals out and dump the rest of it. And so he needed valves that could handle basically high percentage of basically liquefied particles, liquefied dirt. And he had valves that were lasting anywhere from 1 to 3 months. We changed out pretty much his entire plant to CamFlexes. CamFlexes reverse flow, which is not normal for a CamFlex. You're not flowing into the seat, but flowing back. So flowing on the back side of the valve. With ceramics, you know what? He was able to increase his life by about 15 times. So he was getting 1.5 years, somewhere between 1.5 years and 2 years of service life out of these CamFlexes. When he did need to repair them, he was just changing out seat rings. Yeah, I think the plugs lasted maybe 4 to 5 years, but the seat rings which was the last downstream part, was receiving most of the abrasive particles. But the material choice here, along with the fact that it was in most regards just free flowing, low pressure, high particle fluid, worked great in the CamFlex, and he loved it just because it didn't leak. There's no leak paths. There's no packing. There's a real tight packing arrangement. It's all standard environmental packing. So he had no packing leaks. The valve just worked great. So simple application like that, you normally think flowing high percentage of particle dirt. You guess what? It was low enough pressure drop that the CamFlex was a perfect application for it, and it worked great. And there's a lot of applications like that where we can apply CamFlex and not have to go to the high end of the technology spectrum in order to satisfy those applications.
Mm-hmm. Agreed.
The second one is what we call our multi-stage axial flow. And when we start talking about multi-stage, what we're talking about is pressure drop here, guys. High pressure drop across an application will basically up your fluid velocities. So you want to be able to have something that can handle that pressure drop and minimize the fluid velocities in the control valve. Our standard product line for really any type of fluid pressure drop is obviously our Lincoln Log. Lots of them out in service there. Normally, everybody thinks of them as this is your boiler feed water recirc or your feed water startup valve
application.
We've seen it, thousands of times. But these work excellent in other applications where there's high pressure drop and in train solids, because these are basically dirty service valves. They have the ability to pass large size particles through them and a lot of particles as well. And in the, I have these installed up in the North Slope of Alaska for produced water applications. We're seeing, 2, 3, 4,000 psi pressure drop across the valve with entrained sand. And normally the control valves that you'd see in those applications aren't lasting, maybe 3 to 6 months. These are lasting, 18, 24, 30 months. They're between any type of service. And we have the ability to do different materials, duplex, tungsten carbide. And then, the one next to the Lincoln Logs there on the right is the 77, our 77 design, which you see on high pressure separator applications and the like, where you're seeing hot systems, high pressure drop, catalyst fines in the fluid, extremely abrasive services. We're getting, again, multiple year service lives out of these valves without maintenance. So these are the types of applications where you say, I have high pressure drops and I need to be able to control the service of that pressure drop. How am I going to do it? Mm-hmm. We've got the ability to do it in clean service. How do we apply this into a dirty service or a particulate service application? And again, you have the technology. We just do some trim modifications material wise, and we come out with a great valve for the application.
Okay, so you're not reinventing the wheel. You're using existing technology and just tweaking it a bit. Yeah.
Exactly. And honestly, these two valves, both the Lincoln Log and the 77, they're pretty much cataloged items. I mean, they're still in our service portfolio, but they're really catalog items. They've been fully designed and developed. There's not a 6-week engineering action that needs to take place every time we sell these. We actually can ship these Lincoln Logs in 8 to 10 weeks out of our aftermarket center in Houston. So wow. These are something that are really something that we're having to apply more and more because of the changes in service conditions of our customers. Okay. Lastly, I'm going to pull this off, but you can see that here. This is basically a whole engineered portfolio that's designed around our erosive service. You've got the first one is the 71,000. You've got the 73,000, the 74,000. So you've got these different valve models that we use, but they've all been designed specifically for certain types of erosion. And again, these are valves that we aren't applying 100% of the time. They don't need to be specified 100% of the time. But in the applications where it's absolutely necessary, these are the valves that go into service and last for 5, 10, 15 years and handle those services. And so you can see we've got a bunch of different types of flexibility here. But kind of some of the things I want to talk about is you can see a lot of different valve geometries here. And here's where we start talking about angle of impingement and full flow through the valve. So you can see the first one is the 71, is this one right here. Yeah. This one on the left, I mean. Mm-hmm. And we've had that one for 30 years. That was been our mainstay, heavy duty, heavy guided trim design that was great for those applications where you are going to have a lot of particulate. At one point, we wanted to get more life out of it. And so we started looking at other things we can do. The one in the middle is the 73,000. It's our sweep angle design. Sweep. And you can see that it basically looks like an elbow with a valve plugged in the middle of it. And that design is a great design when it comes to minimizing the angle of impingement, because you can take your fluid and it flows very smoothly very laminarly through that control valve, and it's going to limit the amount of damage that is imparted on the valve as it runs, which means it has a good service life. It means it's able to shut off, and it means it's able to do those things for an extended period of time without a lot of maintenance. The one on the right is our 74 design, where we've spent a lot of time over the past couple years standardizing on it, and for extremely severe erosive surfaces, and you can see it's the way it's been designed. It's a very heavy design. It's a design that we can put a bunch of different types of trims, styles, and trim materials in to handle those applications. And it's not so much finesse type like the sweep angle with keeping the laminar flow. This is more brute force, as well as physically directing the fluid stream into the areas you want it to go to minimize the damage.
Yeah, I'll tell you, those are, to me, that slide you're showing there is some of the best kept secrets in the Masoneilan portfolio. I mean, those are really awesome engineered solutions. And, I know the CamFlex is a cataloged item. We inventory a couple $1 million, $3 to $4 million of inventory of Masoneilan, and a couple million of it is CamFlex. Familiar with the Lincoln log, familiar with the angle styles, but that sweep in that last one there, that's pretty unique stuff right there, Joe.
Yeah, and there, like I said, this is 3 of maybe five different designs that we have. So
and you've got more, right? There's more.
We do. The 75K is built specifically for tank drain. It's actually the actual trim is outside the valve. So the seat, the plug and the seat actually are outside the valve, and when the valve opens, it actually extends the plug down into the tank and basically drains inside there. So there's actual no any pressure drop is taken outside of the valve. So it's another specialty design. It's all designed around what is the specific application and the engineered types of service conditions that you're seeing. So
cool. So I think what we're to kind of wrap things up, right, is we've gone over the cause of erosion, and we've gone over the effects of erosion, and we've shown the solutions, and you've shown some standard products, and then you've gone a little bit into some of the best kept secrets of Masoneilan. And I've been selling Masoneilan, working with Masoneilan since 1997. Before that was with a competing brand, and so I know a little bit about some of the competition. And basically, we always so the insider joke around the rep network sometimes is, hey, Masoneilan has some of the best kept secrets. We'd like to tell more people about them. It's like, hey, come on, man. You guys make a lot of really cool solutions to some really difficult problems out there. So
yeah, I think just back in the 10 years ago, 12 years ago, you didn't see the applications in the quantities that we're starting to see over the past few years. And so I think, yeah, they were best kept secrets because, you know what, they weren't being applied as heavily as they are now. But you know what, our customers are changing the way they do business. Our customers are, increasing their efficiencies, and to increase their efficiencies, sometimes that means higher temperatures, higher pressures, different types of catalysts, different types of processes. All of those things change the way we normally look at the market, the way we normally look at what an application is.
The way you solve the problem, what the solution is, right?
Exactly. I mean, I really believe that long gone are the days where you walk into a customer and you say, hey, you've got a water application. What's the temp, P1, P2, and temperature? I'll give you a quote. I think those days are kind of gone, because if anybody can solve that application, really,
Yeah.
The question is, why is he having a problem now? And say, what are you seeing now? Why are you seeing it? And how can we address that specific problem? And that's again, that's why we have the breadth of product. I always go back to, if you can't understand the application, then you can't understand what valve to put in. I mean, honestly I could put CamFlexes in everywhere. And our CamFlex line goes up to 18-inch. Great, I'll put CamFlexes in every application. Is it gonna work? No.
You just made John DeVoe real happy with that statement.
I know.
I'm the product manager for the CamFlex, which was a prior interview. So
Yeah.
Anyway, hey Joe, thanks a lot for coming on. That's Joe Lewis. That was an awesome talk about erosion. Joe, I really appreciate you coming on to the podcast.
Oh, I'm glad to be here.
Yeah, really cool. And hey, folks, you have an application out there for a challenging application, erosion or other challenges, call us at Eastern Controls. We'd be happy to help you. Thanks again, Joe.
Thanks, Bill. Great talk.